Here's an example where we ask the question, is this set of polynomials a basis for P2? And the set is x squared plus 1, and 3x. You can see the answer is no. But let's talk about it for a minute. P2 are the polynomials that are degree less than or equal to 2. So it looks okay at first. It has x squared, it has x, it has some extra stuff, but that could be okay. It has a 1, and it actually has 3 vectors in it, 3 polynomials. So that's the right number of vectors since the dimension of P2 is 3. And it has polynomials of all the powers. But then there's several problems. First, we notice that the third vector is just a scalar times the first, x and 3x. That is always going to make any set of vectors linearly dependent. If you ever have one of them being a multiple of the others, or a linear combination of the others, including just a multiple of one other. So that means it has to be linearly dependent. And that means it's not a basis. A basis has to be all 3 things: independent, span, and have the right number of vectors in it. Of course, we also know that 2 out of 3 are good enough. So since it's linearly dependent and it has the right number of vectors, that means that it can't span. If it did span, then it would have 2 out of the 3, but it does not have all 3, so also can't span. So that's more than you needed to say for this problem. As soon as you notice that it's not linearly dependent, the answer would be no. All right, so let's look at this next one. And this one is about R3, and we have 3 vectors, 0, 1, 0, 1, 0, 1, 0, 3, 0. Is that set a basis for R3? So the answer is no. And this time you could do it a couple of ways. Either notice that 0, 3, 0, the final vector there, is equal to 3 times the first one. Again, that's not allowed. If you're going to have that, then it's linearly dependent. Or you could make those vectors into the 3 columns of a matrix, also 3 rows, and row reduce it. And when you row reduce it, let's see, what I did here was first I switched the second row with the first row, and then I noticed that the second row and the third row were the same, so I subtracted one from the other and got a row of zeros. And now I see that I have 2 pivots. It's in row reduced echelon form, and 1 free variable. All right, so a free variable means that there's an infinite number of solutions to the homogeneous equation and linearly dependent. Remember, independent would be no free variables, but was dependent. So again, doesn't span. Another quick way of doing this, since it happened to be a square matrix, I could have taken the determinant of it, and the determinant does come out to equal to 0. But now, notice that these 2 problems are really the same, number 1 and number 2, because the second problem, number 2, is just writing the polynomials from number 1 as their representative column vectors using the standard basis for P2, which goes 1, x squared. So I write x as 0, 1, 0 because it has 0 constants, 1, x, and 0, x squared. X squared plus 1 is 1, 0, 1 because it has a 1, no x, but it has 1 x squared, and 3x is just 0, 3, 0. So I've answered the question probably 1, 2, 3, 4 different ways now that the answer was no. And you can do any of those. There's a lot of different possible ways of answering the same question. Let's look at another, but I have to find it. Okay, here's an example. Is x plus 3, and 5x minus 1 a basis for P2? Okay, so this one has answered no, but there's even a new way of answering this question. We could have noticed that it has 3 vectors. That's the right number. Dimension of P2 is 3. We also could notice, we could also do a row reduction or find a determinant, but real fast, there's no x squared in it. And the only way you can possibly get all the vectors in P2 is if you have some x squared to work with in your basis. So it can't span P2, so the answer is no. And then we know it has to also be linearly dependent, because if it can't span but it has the right number of vectors, then it can't have that third one. How about this one? X squared plus 1, x squared plus x, 3x, and x minus 1. Is that a basis for P2? Well, the fastest way to answer this one is no, because it has the wrong number of vectors. Dimension of P2 is 3. Remember, dimension of Pn is always n plus 1. And this one has 4 vectors. So, too many vectors. We don't know anything about its span or its linear. Well, we do know it's linearly dependent. We don't know about the span, but it has to be linearly dependent because it has more vectors than the dimension. Right? That's the same thing as having more vectors than the number of components, because the dimension is the same thing as the number of degrees of freedom. So, too many vectors. Next one, 3x squared plus 2x and 5x minus 3. Is that a basis for P2? So again, these last two, they don't have the easy way out, which is to notice that it has it's missing some power of x. This one has all the powers of x, but it only has 2 vectors. So it has to have 3, since that's the dimension, n plus 1 if it was Pn. So the answer is no again. And in this case, if it has too few vectors, we know it can't span. It might be linearly independent, but definitely can't span. Then we have, let's see, x squared plus 1, 1 minus x, and x. Is that a basis for P2? Finally, here's one that the answer is yes. So looking at it, we know it has the right number of vectors, 3. It has all powers of x represented, but we still don't know if it's linearly independent and therefore spans, or spans and therefore is linearly independent. So the quickest thing is to check that linearly independent is holding. And the quickest way to do that, since it has the right number of vectors, and that means it has the same number of vectors as the dimension, that means that if we write down those vectors as columns representing them using the standard basis, then it will be a square matrix. So we'll have 1, 0, 1 for x squared plus 1, 1 and negative 1 for 1 minus x, and just 0, 1, 0 for the x. And you take the determinant of that, you get 1. It's not equal to 0, so that means that it does have that unique solution, and therefore it's linearly independent. And then since it has 3 things, it also spans. That means it's a basis. Here's one more, just to make it a little bit fancier. Is this one a basis for P3? It's got 1, 2 plus 3x, 4 plus 5x plus 2x squared, and 7x minus x squared plus 4x cubed. So the dimension of P3 is 4, and it has 1, 2, 3, 4 vectors, which are polynomials. And that means we have to check does it have linear independence. So we write the matrix for that using the representatives in the standard basis. So 1, 2, 3, 4, 5, 2, and 0, 7, negative 1, 4 for the 4 polynomials. And the determinant of that is 24, not equal to 0. So that means we know that it's linearly independent, but therefore it also spans because it has the right number of vectors.